First of all, I'm sorry not to be there in person. I really hope that, yeah, very soon I'll be able to see a lot of you again at a physical conference. But we'll do our best with technology. So, like Ohad said, my background is pretty mixed. The reason I got interested in automatic differentiation was primarily because I took on the task of implementing a new compiler for the STAM probabilistic programming language. And at the time, I felt like I knew what probabilistic programming was about. But then when I started implementing this compiler, I quickly realized that much of the efficient implementation of inference algorithms for probabilistic programs depends on a technique called automatic differentiation. It's a technique to calculate derivatives of functions. And I realized this technique is actually quite complicated and quite tricky, and I didn't understand it well enough. So that's why I started digging and talking to a lot of people. And I think I'm finally sort of at a point where I'm starting to get an understanding of the topic that I'm somewhat happy with. So my title really should have been some remarks about aspects of the mathematical foundations of automatic differentiation. I don't at all mean to suggest that I fully understand everything, but hopefully I'll be able to convey some useful intuitions and ideas in this tutorial. So first, let me give some motivation. Very simple motivation for automatic differentiation arises the moment you try to fit any sort of regression problem.
Recording in progress.
So this can be as simple as a linear regression, but generally it tends to be a more complicated regression problem that we see in practice, like a neural network regression. But the basic idea is you have some data points, right? You see them here, you have some data points, and you want to fit some curve through the data to extrapolate or interpolate beyond the data. Right? And the way that we typically do that is we write down some cost function that measures how well this regression function fits our data. So in this case, it can be a sum of squared errors between the regression line and the data points. And then we try to minimize that cost function by sort of tuning the parameters of this regression function. In case we're working with a linear regression, there are only two parameters, namely the slope and intercept of the regression line. And we tune those a bit to make the performance of this model better by making the error smaller or the cost smaller. And if we keep doing that, making it smaller and smaller, we hope that at some point our regression will actually give useful predictions and useful extrapolations beyond the data. Right? So what that means mathematically is often that we calculate the derivative of this error function or cost function. You see it graphed here for the sum of squared errors. And then we take little steps in this cost function landscape and we try to minimize it. And we do that generally in a greedy way by taking little steps in the direction in which the error decreases fastest. And that direction is measured by the gradient or the derivative of the cost function. So what we tend to do is we tend to follow the derivative downhill until our performance gets good. So you immediately see that to fit regression models using maximum likelihood estimation or to just solve mathematical optimization problems on continuous parameters, we often encounter a need to calculate derivatives of the function we're trying to optimize. For example, a likelihood function. So we need a good technique to calculate derivatives of these cost functions, and these cost functions tend to be implemented as a piece of code, right? They're a program. So we want to calculate derivatives of functions implemented as programs. And it turns out that the best technique we have to do that is automatic differentiation. And you may have also heard about reverse mode automatic differentiation under a different name, namely backpropagation. So that's the very, very brief motivation for this tutorial. Here's a funny cover of a children's book I saw the other day. Turns out that people now consider this optimization technique, it's typically called gradient descent, so important that they're writing children's books about it. So hopefully this convinces you that gradient descent and therefore automatic differentiation are important. Okay, now let's zoom out a little bit. I would like to note that there are many, many perspectives on automatic differentiation. It's a topic that has a very long history, going back at least to the 60s, when Wenger introduced forward mode, and then the 70s and 80s when various people independently discovered reverse mode AD, and it was studied in the scientific computing community, and then they had their own automatic differentiation conferences. Then it was picked up by the machine learning community, so they developed these languages or these libraries called TensorFlow and PyTorch and others. It was picked up by Stan in the statistics community, which is where I saw it. And then very recently, it's also gotten the attention of the programming languages community. So in some ways, a lot of what I'll say in this tutorial will fit in that last line of work. So it'll be studying automatic differentiation from a programming language perspective. But you have to understand that this is actually quite a new perspective, and it's not as mature as many of the other perspectives on the topic, because we have been a bit late to the game as a community. That said, I think there are very, very interesting programming language aspects to automatic differentiation, as I'd like to, hope to convince you in this tutorial. Okay, so the perspective I'll be pushing, and that I hope to convince you of in these 3 sessions, is basically the following. Summed up in one slide, and hopefully by the end you'll understand what this slide means, and you'll be somewhat convinced of its message. And it's the idea that I've been calling combinatory homomorphic automatic differentiation. And my perspective is really that a lot of automatic differentiation, if not all automatic differentiation, should be or can be this sort of combinatory homomorphic automatic differentiation. And now, what do I mean by that? Well, the idea that I'll present is that we can view programming languages, particularly functional programming languages, as certain freely generated categories, or certain initial categories in bigger classes of categories. And as such, they have a certain universal property. It means that we can define functors out of programming languages in a certain way, if we meet certain conditions, if we have a structure of a similar kind as our programming languages. In particular, using this universal property of a functional programming language, we can define various automatic differentiation algorithms using this universal property. So the automatic differentiation algorithms become a certain kind of structure preserving functor from a programming language. So whenever I write homomorphic or say homomorphic functor in this talk, I mean just a structure preserving functor. So say that our programming language is a category with products, then a homomorphic functor on that thing will be a product preserving functor. If it's a Cartesian closed category, then a homomorphic functor will be a Cartesian closed functor. Okay, so automatic differentiation will be one of these homomorphic functors. The semantics of our language will arise as one of these homomorphic functors as well. And so will the correctness proof of automatic differentiation, which makes use of both of these previous functors, right? It makes use of the definition and the semantics. And I'll show you that this works for at least 4 different automatic differentiation algorithms and some more. We'll see that by varying the categories that we work with, by varying the base cases in the definition of automatic differentiation, we get different canonical automatic differentiation functors together with their correctness proofs. Okay, so this perspective is something that I developed in talking to a lot of people. First of all, Sam Staten and Matthijs Vákár, when we were working on so-called dual numbers, forward mode automatic differentiation. A lot of the crucial ideas were already present in our work together, and I'm sure that a lot of other people had noticed it as well. I also remember talking about it with Ohad and Ohad Kamar and many others. I don't think this is a fully unique idea, but I think it's nice to take this idea of automatic differentiation as a homomorphic functor seriously and see how far you can push it. And it brings you surprisingly far. After my work with Sam and Mathieu, I started working with Fernando Lucatelli Nunes, who's a very strong category theorist, and he's really been expanding the scope of the automatic differentiation algorithms and the language features we can apply this technique to. He's does really nice work on mathematical foundations for applying this technique to automatic differentiation for expressive language features, and I'll show you some of it in these sessions. And recently, we've been working together with Gordon Plotkin on applying it to reverse AD for languages with recursion. And then finally, I'm working closely with Tom Smading, who's been doing some really nice work on showing how you can implement this technique efficiently. And he's been studying the complexity of these automatic differentiation algorithms. And ultimately, the goal will be to write an efficient implementation that runs on GPUs via the Accelerate GPU programming library in Haskell. And for that, we're working together with Gabriele Keller and Trevor McDonald, who are the developers of Accelerate and real experts. But like I said, I've been working with many more people on this, and I hope you don't feel left out if some of your ideas are in this talk as well. Give a shout. So some of the topics we'll cover in this tutorial will range from very basic topics like why we should care about automatic differentiation and basic automatic differentiation algorithms to a more categorical story that will be the meat of this tutorial. So that will be the story about programming languages as free categories and automatic differentiation as structure preserving or homomorphic functors, and some correctness proofs via logical relations arguments. And then finally, we'll talk about some practical considerations like how you implement this efficiently and how you generalize it beyond AD, because a lot of the ideas that are present here aren't specific to automatic differentiation at all. So let's dive a bit deeper. Why do we really want to compute derivatives? I've given you one example of regressions. And that example was an optimization problem, right? Say that we want to solve an optimization problem on a continuous space. Then often we use some greedy algorithm that takes steps downhill in the steepest direction measured by the gradient. So that leads to a sort of gradient descent optimization algorithm. And we have many variants of that, right? We have Adam grad, and variants that take momentum into account. We have higher order optimization algorithms like Newtonian methods, quasi-Newtonian methods. But what they all have in common, other than that they're very successful in practice, is that they all depend on a calculation of derivatives of the function we're trying to optimize, right? Another context that is quite different, where we turn out to need automatic differentiation, and this is the context in which I first encountered it, and that's a context that we see a lot in probabilistic programming, is when we want to do Bayesian inference, right? It turns out that to calculate a posterior distribution for a model that has continuous parameters, some of the best techniques we know to solve the complicated integral that you need to solve, or the Markov integration problem that we need to solve, turn out to use derivatives. So that's a bit surprising that sometimes you need to differentiate in order to be able to integrate a function. I'm thinking in particular of techniques like Hamiltonian Monte Carlo and automatic differentiation variational inference and its variants. And recently, even a very successful Bayesian inference algorithm for discrete parameters uses gradients, and it's called Gibbs with gradients. I don't know if you've seen it, but it's an algorithm I'm very interested in. And then finally, often you're in a situation where you want to solve systems of nonlinear equations, and we often do this with Newton-Krylov methods, which also use derivatives. So we've seen that optimization shows up in, well, machine learning contexts where we're fitting neural networks, for example, but it also shows up in statistics if we want to do maximum likelihood estimation, and in many more contexts. Solving Markov integration problems shows up in Bayesian inference, of course. So in applied statistics and probabilistic machine learning. So here you're seeing a graph of a recent coronavirus model. It's the official British government model for coronavirus forecasting, and it uses Stan under the hood. So people do actually use Bayesian inference and therefore automatic differentiation in practice at the moment to solve important societal challenges. And then finally, these systems of nonlinear equations that we often want to solve, for example, can arise from discretizations from partial differential equations that come from physics that we want to solve, that we then turn into systems of algebraic equations using, for example, finite volume methods or finite element methods. I wonder if there are any more use cases of derivatives that you, as an audience, have in mind for being interested in automatic differentiation. If there are any more, maybe you can write them in the chat or shout out. But yeah, I'm always interested to hear what people use them for. I see that Alex Liu suggests in the chat a change of variable calculations, reversible jump MCMC corrections. Yeah. So yeah, maybe you can, if you have a reference for that, maybe you can also post it in the chat. I'd be very interested to see it. But I think the story is that whenever you have a piece of code that implements a function and you want to efficiently calculate the derivative of that piece of code without handwriting code for the derivative each time you change the function, but you automatically want to generate code that calculates the derivative, automatic differentiation might be a good technique to use. Okay. So let's zoom in a bit more on what it means to calculate a derivative, now that we hopefully care about calculating derivatives. So there are some different perspectives on what it means to be a derivative, right? If you've taken some different math classes, maybe all your math classes introduced the derivative in a different way. And it turns out that many of these perspectives are equivalent, but not quite the same, and they tend to be equivalent in finite dimension at least, and sometimes in more general settings, they start to diverge. But for our purposes, as long as we're calculating derivatives of vectors, real numbers, we can use any of these three perspectives, right? So one perspective that we learn about early on when we're taught about derivatives is a sort of geometric perspective. So I guess the first picture that you see of a derivative tends to be of a graph and a tangent line to the graph, right? So this is the geometric idea that a derivative is the best linear approximation to a function in a way. So what that means is if we have a function f from Rn to Rm, the derivative d of f is a function that takes the input x of type Rn and produces a function, a linear function really, that takes in a tangent vector at the input point x and produces a tangent vector to the output, right? So it extends the action of f to tangent vectors. And it does so at each point, at each input point. Right? This is a very beautiful definition and it's quite intuitive, but it's not immediately obvious to me how you distill an algorithm from it. A different definition of a derivative that you might have seen is the analysis definition as a limit of finite differences. And here the idea is that, well, the derivative of f at the base point x, at the primal value x, and when we give it a tangent vector v at x, is, well, the limit of the difference coefficient, different quotients of f evaluated at x plus a little step of size delta in the direction v minus f evaluated at x divided by the length of that step delta, right? And as long as we take that step small enough, then we get a derivative. We start to approximate the derivative. And this is a definition that we can naturally convert to an algorithm, right? And we'll see that that algorithm is well known and it's called finite differencing. We'll look at that next. A very different definition of derivatives, however, follows from a more algebraic perspective. And I think that this is somehow the definition that we often teach to high school students, because in some ways it's so easy. It's so easy to calculate with. And that's the idea of derivatives as a kind of magical recipe that performs a symbolic transformation governed by certain rules, right? So we teach our high school students certain rules like the chain rule and rules for how you differentiate certain primitive operations, like we teach students that the derivative of a sine function is a cosine. And we teach students that to differentiate multiplication, we use the product rule. And then by putting all these rules together, you can mechanically calculate a derivative, right? And we'll see that to implement this algebraic idea, if we implement this algebraic idea in code, we end up with a technique that is automatic differentiation. And that is we end up with automatic differentiation as long as we start not just with a little grammar of functions that use sine functions and multiplications and such, but a more general grammar that allows us to write computer programs with let bindings and all the constructs you normally expect in a programming language. As long as we apply this algebraic idea to such a grammar, then we end up with automatic differentiation. Okay, so hopefully this comic sort of summarizes why automatic differentiation has been so successful. And the idea is really that differentiation is surprisingly simple. It is shockingly simple, that as long as we have a rule that tells us how to differentiate each language primitive, we can calculate the derivative of a composite program by combining all these rules, like the chain rule and the product rule and such. You can contrast this with integration where there isn't such a general recipe, right? Which is why we end up with numerical methods like Hamiltonian Monte Carlo. Okay, so we might have different techniques for calculating derivatives. So you've already seen that we will end up with this finite differencing method that comes from analysis. We end up with at least one automatic differentiation method. It turns out that there are many different automatic differentiation methods. So let's think a bit about what properties of an algorithm that calculates derivatives we find important. So the first that I would mention is that we want to have a low developer cost. In my mind, the main thing that motivates automatic differentiation is that we don't want to have to write custom code that calculates a derivative for each program, right? We don't want to both have to implement our program that is a statistical model or a neural network of some kind, and then manually have to implement a derivative for that thing, right? Because that's error prone and a lot of work. What we want is a method that automatically generates that derivative code. And then we want the method to be highly efficient in time and space, ideally, right? And the reason is that, well, in STAN, we tend to fit models that maybe have 10,000 parameters, maybe 100,000. That's a pretty high dimensional space on which you're differentiating. So things tend to get pretty expensive. Hamiltonian Monte Carlo also isn't a cheap algorithm. So we end up calculating a lot of derivatives before we converge. And the situation is even worse in machine learning. If we're working with neural networks, they can have billions of parameters or even more. So it's quite important that these algorithms scale well in their time and space complexity, particularly if the input of the function that we're differentiating becomes high dimensional. Because it turns out that the main use case that we have is to calculate derivatives of functions that have a very high dimensional input and often a one-dimensional output. For example, the gradient of some likelihood function of a probabilistic model. Now, ways of getting this good time and space behavior is, first of all, to come up with an algorithm that has the right complexity. And then, I think very importantly, we want to reuse existing compiler infrastructures because we don't want to worry about all the low-level implementation details, right? People have already written efficient array processing libraries. We don't want to have to reinvent the wheel just because we're calculating derivatives. Ideally, we'd also like to avoid interpreter overhead where possible. So we want to do as much of the differentiation at compile time as possible and expose as much of the code as we can to the compiler that can then optimize it. This interpreter overhead, it's debatable whether it's super relevant or not. Some methods for AD, as we'll see, require an interpreter, others don't. I think it's an open problem. It's to be seen whether the methods that don't depend on an interpreter are going to vastly outperform the ones that do need an interpreter. But ideally, if we don't need one, I would like to avoid one. Then we want to exploit parallelism, hopefully. The reason, again, is that the models that we often want to differentiate, particularly in machine learning, tend to be big regression models that have big matrix multiplications in them, or Cholesky factorizations, or big operations that we can parallelize. And if we have that parallelism in our source program that just calculates the value of the error function or the value of the likelihood function of the probabilistic model, then we'd ideally like to keep that parallelism in our calculation of the derivative, because the calculation of the derivative is going to be more expensive even than the calculation of the primal values of the program. And to be able to exploit that parallelism, I would like to focus on techniques that generate purely functional code. And there are other techniques that are very interesting as well and successful that don't just generate purely functional code, like the demystifying differentiable programming paper by Wang et al. Yeah, in this session, I will focus on purely functional techniques for this reason. Then I care about having a calculation that is correct. Either we know it's correct because we can prove it's correct, or we can test it, and ideally both. And again, that's easier if we have purely functional code. Then we care about numerical stability. Of course, if you're working not with real numbers, but with floating point arithmetic, we can get all kinds of rounding errors, and they can actually be relevant in practice. We've seen in particular in STAN that Hamiltonian Monte Carlo is quite a fragile algorithm, much more so than these optimization algorithms that use automatic differentiation like gradient descent. And the issue is that Hamiltonian Monte Carlo is simulating a physical system of which the energy needs to be conserved. And if the derivative calculations are too bad, we end up going off the Hamiltonian trajectory. So we end up not preserving the energy, and then the algorithm breaks. So we see that this good floating point behavior and numerical stability is really important, particularly in probabilistic programming. Then we want the algorithm to be extensible to new features, modular. And this talk achieved that by looking at local well-typed code transformations. And that sort of code transformation will also make it easier to prove that the transformation is correct. And finally, I would like this technique to be generally applicable. And the reason for that is that ideally, I'm hoping that we'll have a future where people will write an arbitrary piece of code in a general purpose programming language, and that the compiler is able to differentiate it pretty efficiently. And to give you an example that shows that this may be important, I would like to go back to when I was doing my PhD in Oxford. There was a group in physics that had a very impressive simulator of the standard model. And what they really wanted to do is they wanted to learn through that simulator somehow. They wanted to fit their simulator to data and learn something about the parameters in the standard model from their data directly. And the way they wanted to do that ideally was to use some sort of probabilistic programming technique to do Bayesian inference through their code. And it was totally infeasible at the time using most methods because we couldn't differentiate through that code. So it would have been very nice if their simulator hadn't been written in C++, but had been written in a language that people could actually differentiate through. And even though they didn't have automatic differentiation in mind when they originally wrote that code, they later changed their minds and realized that they would quite like to differentiate through it. So this is why I would like the technique to be generally applicable. Are there any more properties that we really care about? If so, feel free to post them in the chat or call them out, but have a think for yourself about, what properties do we really care about when we calculate derivatives? I see that Alex Liu has posted some references, by the way, for his other application of AD to change of variable calculations and reversible jump MCMC. So if you're interested, you can find those in the chat. Okay, so now I'd like to zoom in on finite differencing. And we'll be very quick about it because we'll see that it's not a very suitable technique for calculating derivatives generally. So finite differencing was this differentiation algorithm that didn't come from algebra, but from analysis, right? And the idea is, I've written here in some kind of pseudocode, sort of pseudo Haskell. You should read this as a differentiation is a function that takes a function from A to B, where A and B are sort of vector spaces, so things on which we can add and do scalar multiplication. And it produces a function from A to B, where the first A you should think about as a primal input to A, so just a regular function input. The second A you should think about as a tangent vector at the input. Right, and the derivative of f at point x evaluated on tangent vector v is obtained as this difference quotient for some small number delta. Right, and as long as we take delta small enough, the idea is this should be close to the derivative. Now, does anyone see any problems with this technique? Maybe have a think about why you might not want to do this. Well, one thing that is bad is
you divide it by very, very small numbers. So
yeah,
numerically speaking, it's unstable.
Yeah, and why is it unstable?
I mean, you have a ratio of a number which is I mean, you have 0 divided by 0. I mean,
yeah, there are many things that are bad here, right? There are many things.
Two very small number divided, it can't go well.
No, I mean, one thing that's really bad here, for example, is that we're adding a number x that is quite large, presumably, to something that's very small, right? Delta was very small. So we're adding something very small to something pretty large. So we're losing a lot of precision there. And then we're subtracting two numbers, f of x and f of x plus something small from each other, where those two numbers are almost the same, right? So that can't be good either. And we also lose a lot of precision. So, and there are probably more ways in which this is bad, but yeah, numerical stability is a huge problem in practice with this method. Another issue could be that it's not efficient in the way that we really care about, right? So if we have a function f from Rn to Rm, and we want to calculate the full derivative using this technique, well, what we see is if we stick in a basis vector for the tangent vector v, we calculate some column of the matrix of derivatives using this technique, right? And we do that using two function evaluations of f. So we can efficiently calculate a column of the matrix of derivatives, even if it's not very numerically stable. But if we want to calculate a row of the matrix of derivatives, yeah, that's a different story. If we want to calculate the whole matrix of derivatives for a function where n is large and m is small, which is the typical application domain for automatic differentiation, yeah, we get a time complexity that scales in n, right? And n is going to be enormous usually. So this is also a pretty inefficient technique. We'll see, however, that it is still useful, and we do end up using it in STAN, and I think a lot of practical implementations of automatic differentiation use finite differencing because it's a nice target to test automatic differentiation against. Because finite differencing is so simple, right? It's hard to do it wrong. So as long as we build in a tolerance for numerical stability errors, or if we work with a lot of precision, then we can still test against finite differencing quite well and make sure that our more complex automatic differentiation algorithms are correct. One more feature of this algorithm that I'd like to highlight is that it's quite cool that it implements differentiation as a higher order function. Right? The only way that f is used in this definition is that f is given some inputs and we examine the outputs of f. So f is a black box as far as this differentiation operation is concerned, a black box that sends inputs to outputs. Okay, let's proceed to automatic differentiation. So first I'll look at a very simple forward mode algorithm. So this is an algorithm that Conal Elliott proposed, and I've also looked at it with Tom Smeding and Fernando Lucatelli Nunes. And I think some more people have considered it, but we'll see that it's not incredibly efficient, this algorithm. But why it's interesting is because it's a useful stepping stone to reverse mode AD. Okay, So again, we have an algorithm that calculates one of these columns of the matrix of derivatives in an efficient way. But now differentiation is no longer a higher order function, but it is a meta program. And what I mean by that is to implement this algebraic idea of differentiation as a symbolic transformation, we need the operation to have access to the source code of our program. So the way you can read this is differentiation is a function, this bit of pseudocode says differentiation is a function that takes code for a function from A to B, where A and B are vector spaces, and it produces code for a function that takes an A and produces a linear function from A to B. The linearity of the derivative here isn't terribly important, but I just wanted to annotate it to point out, yeah, derivatives aren't just any functions, but they tend to be linear in their second argument, right? That's why we can represent them as a matrix. And now the way we proceed to implement this basic automatic differentiation algorithm is just by implementing all the standard high school recipes, right? We say that the derivative of a composition is governed by the chain rule. So the derivative of f and g is a function that takes a primal value x and a tangent vector v, and it first evaluates the derivative of g at x on v, and then it evaluates the derivative of f at g of x on the result, right? And similarly, the derivative of a sine function is just a function that sends an x and the tangent vector v to the cosine of x multiplied by the tangent vector v. And the tangent vector v in this case is going to be one-dimensional because sine is a function from R to R. Similarly, for multiplication, we see the product rule for derivatives. So this is much more numerically stable already than our previous attempt. So in that sense, it's an improvement. In some other ways, it's not much of an improvement. Does anyone see any problems with this, this bit of code? Prakash says it's restricted to known functions.
You've
Yeah,
got an
absolutely.
awful lot of cases in there.
What are you saying?
You've got a lot of cases going on.
Yeah. No, that's true. And that's very annoying, but that turns out to be fundamental to automatic differentiation. It's a lot of work to develop automatic differentiation libraries. And that's, I think, part of the reason that some of the very successful ones have been developed as big open source collaborations, right? That where everyone who needs a new function can add the derivatives of that primitive function. But yeah, you need a case for each primitive operation. And like Prakash said, that means that we can only differentiate known functions. And this is true for all automatic differentiation libraries. Any more problems?
What do you do with higher order code?
Higher order code.
Abstraction.
Oh yeah. Higher order code we're not dealing with yet, but it turns out that we can deal with it, and we'll look at that later. But yeah, it's not so obvious what to do with higher order code, right? Because the way I came up with this was just to implement all the things we teach our high school students about derivatives, right? And we don't teach them about differentiating higher order functions. Yeah, absolutely. And Xavier Rival was saying we have high cost with large products, so an exponential blow up. Yeah, that's particularly true if the domain of the function is high dimensional, right? Because this code is going to calculate a column of the matrix of derivatives in a relatively efficient way, but yeah, you need to evaluate it once to get each column, right? So if you want to calculate a row of the matrix of derivatives, that's not very good with this technique. But there's one more problem that I see in this code, and that is that in the chain rule, we see that to calculate the derivative of f composed with g, we don't just need the derivative of g, but we also need g itself, the function value of g itself. So this code can be made more efficient by pairing up the function value of g with its derivative value. And often we see that there are shared subcomputations between the function value of g and the derivative value of g. So we don't just want to pair them up, we also want to use let bindings to share the common subcomputations between g and its derivative. Okay, so if we do that, we end up with this bit of code. The types have now changed a little bit. So you'll see that we now have an operation that takes a function from A to B, where A and B are vector spaces. So it takes the code for a function from A to B, and it produces the code for a function that takes an x of type A. So this is a function value of type A. So we call that a primal value of type A, usually in automatic differentiation. And it produces a pair of a function value of type B, which is going to be just the value of the original program, together with a linear function that takes a tangent vector at A and produces a tangent vector at B. Right, so now with these new types, we can again write down the chain rule in this new form, and we can write down the derivatives of primitive operations. So for example, the derivative of multiplication, or let's take sine. The derivative of sine is a function that takes an x, produces sine of x, so the function value, together with a function that sends a tangent vector v to multiplying with cosine of x. Okay. So now it can be a little exercise for you to do at home or in your break to see whether you can naturally write down how this code would extend to differentiating tuples and let bindings, and make sure when you do that you preserve sharing, right? So as long as you see that this is what the types have to be, there's basically only one thing you can do to calculate these derivatives. And you'll see that it's not that hard. Yeah, the answer will be in the slides that I'll send around. I won't say much about it now, but what you end up with is a technique that's actually reasonably okay for calculating derivatives of functions from Rn to Rm, where the dimension of the codomain is large and the dimension of the domain is small. The reason is that this technique calculates a derivative. It calculates a column of the matrix of derivatives with ON. It calculates the full matrix of derivative with an ON time complexity overhead over the original function. So it calculates a column in the same time complexity as the original program. And what we'll see, though, is that this technique has a bit of an unnecessary space overhead that we can get rid of. And the reason is that we are storing all the intermediate values of the original computation. And we're going to use them later then to calculate derivatives. And it turns out that we don't need to store all of these intermediate values. And there's a nice trick called the dual numbers trick that we can use to make the space complexity of this algorithm a bit better. One more property I'd like to note is that this algorithm is actually somewhat friendly to your compiler. You can integrate it in your compiler because it is not going to spit out enormous amounts of code. Because you see that the derivative of each subterm occurs exactly once in the code for the derivative of the bigger term. And because of that, we'll see that the code that it generates is proportional in size to the code size of the original program. So you're not going to generate enormous amounts of code. Here's a little example program on which we can see a bit better what this technique really does. So we have a program that takes a single real number as an input and calculates 3 real numbers. So you can think of these real numbers as implemented as floating point. And I've taken a very simple program to make very clear what this technique does. It's just a bunch of let bindings that each do one operation in a row. So we calculate y by multiplying x by 2, and then we calculate z by multiplying x with y. W is cosine of z, and then we return a triple. Right, so what a forward AD transform program then looks like is it's a function that takes an x that's a single real number, and it produces a pair of 3 real numbers. So this is going to be the function value of the original program, together with a forward propagator that calculates the derivative, or calculates a column of the matrix of derivatives, right? So it takes a tangent vector at the reals, so that's a single real number, and it produces a tangent vector to the output, so 3 real numbers. And what we see is that if you do a little bit of syntactic simplification, the algorithm I just wrote down generates this code. So it just runs the original code first. We tend to call this the Primal Pass in the automatic differentiation literature, you see that this is really identical to the original program. And then it returns a pair of the return value of the original program together with a function, a linear function in this case, that takes an x prime, so this is a tangent vector to the input, and then it goes through the program again in the same order, but now it replaces each operation, each primitive operation, with its derivative, and it composes them using the chain rule, right? So we see that z is computed from x and y using a product. Here we see that z prime is computed from x prime, y, x, and y prime using the product rule for differentiation, right? And cosine gets sent to minus the sine. So we see that this way, by using a combination of the chain rule for derivatives and recipes for differentiating primitive operations, we generate this tangent pass after the primal pass that then calculates the derivatives. And here we immediately see a bit of an inefficiency in this algorithm, right? We see that, hey, this value y prime only depends on x prime. So we could have calculated y prime much earlier on. And then after we've calculated z, we don't need y anymore. So we can, if we interleave the tangent pass and the primal pass, we'll see that you don't need to keep all of these intermediate values in memory for as long. So that's an algorithm we'll look at in a bit, a so-called dual numbers approach to forward AD, where we don't first do the primal pass and then the tangent pass to calculate the derivative values, but we do the primal pass and the tangent pass in an interleaved way. That way we free up memory more. But overall, we still perform the same number of operations. So the time complexity isn't any different. Is this clear? Are there any questions at this point? No?
So I have one, maybe?
Yeah.
So some of these transformations are very standard in compilers, right? It's kind of detecting the information flow and removing it. So,
Yeah.
You know, why do we need a specialized AD law for that? Why can we not use a kind of a run-of-the-mill compiling technique?
Yeah. So maybe a
these?
standard, maybe a smart compiler can already automatically optimize forward AD in this form to this interleaved form, if that's what you mean. Yeah, this more efficient dual numbers form. Sure. And I think that's generally going to be my perspective, that I think we really need to be smart about what's fundamental to AD and what's generic to compilers. And I think so far, people have been building these big AD systems without very much input from programming language people initially. And nowadays, there are many more programming language people involved. But I think some of the concerns that we have in AD are much more general concerns. And you see that people are re-implementing standard, I don't know, common sub-expression elimination algorithms and all the things that a compiler should already be doing. So we need to have a separation of concerns. That's why I want to keep the AD algorithms really simple and then pair them with a good optimizing compiler. Exactly, that's my hope at least, that we can get efficient systems that way. But I don't think we're there yet, to have that nice separation of concerns. But that's a very good question. Okay, so now I'd like to talk about reverse AD, which in many ways is a more interesting algorithm. Because it's the algorithm that's going to be efficient if the input is high dimensional and the output is not so high dimensional, which is generally the application that we care about, right? We care about differentiating or calculating the derivative of a function that has a million-dimensional or billion-dimensional input and a one-dimensional output. And the algorithm I'll describe here is something that Conal Elliott introduced and Abadi and collaborators also considered in this differentiable Curry workshop paper. And I've been looking at it with Tom Smading and Fernando Lucatelli Nunes as well recently. And it's a really pretty algorithm. And we hope that we can get it to the point where it's a very competitive implementation, but I have to be honest and say that we're not there yet. But I'm hopeful that we can get it to the point where it's competitive with all of these non-purely functional systems or all the systems that people use in practice, like TensorFlow and PyTorch and that maybe are a bit more complex. Okay, so the starting point is again our forward mode algorithm. And we saw that our forward mode algorithm calculated the derivative of a function f from Rn to Rm as a function that takes a primal value of type Rn and it returns a linear function from Rn to Rm, right? And now what reverse mode AD will do is it won't calculate the derivative, but it will calculate the transpose derivative. So what you're seeing here is we're swapping the n and the m here in the derivative, right? So we're transposing the matrix of derivatives. And the reason that we're doing that is because we want to calculate not a column of the matrix of derivatives efficiently, but a row, right? That's what we care about doing efficiently. And transposition swaps columns and rows. Now, why is it called reverse AD? Well, the reason is that transposition is a contravariant functor in the sense that it swaps operations. So the transpose of A multiplied with B is the transpose of B multiplied with the transpose of A. So we're going to see a sort of reversal of operations in reverse mode AD. And that's because we're calculating transpose derivatives rather than derivatives. Okay, so we see that in the types here as well, right? So what it does is it takes code for a function from A to B, and it produces code that takes an A, produces a pair of a B, and a linear function from a B to an A. And now we see that the chain rule has swapped in order, right? So we see that to calculate the derivative of f and g, we now need to first apply the derivative of f and then the derivative of g, right? So you can compare this to the forward mode code. So the f and the g have swapped. Not much else has happened. The other thing I'd like to note is that the derivative of addition now isn't addition anymore, but it is pairing. So the other thing that happens if you look at a matrix that adds two things, that's a row matrix that has two ones in it. If we transpose that, we get a column matrix with two ones in it, and that's the diagonal. It's something that duplicates something. So the derivative of addition is duplication. And we can similarly calculate what the derivatives are of all other operations. We see that the derivative of sine hasn't changed. And that is because sine is a one-dimensional operation. It goes from R to R. The transpose of a one-by-one matrix is itself. Right? So again, we can differentiate other first-order functional code. And now the thing to notice is that the derivative of a projection becomes a kind of injection. So the derivative of projecting on the ith component becomes generating a sort of one hot tuple that has a bunch of zeros in it and has v in it in the ith place and otherwise zeros, right? And that is, again, because we're implementing the transpose derivative of a projection matrix. You can write down a projection matrix and you can transpose it, and you can see what the transpose should be. Similarly, we can differentiate let bindings, and we're quite happy. We get a nice algorithm that works for first-order programs. And this is what Conal Elliott did, really. Except now I've written it down in terms of the lambda calculus instead of sort of categorical combinators like he did. Okay, so the complexity of this algorithm is much more similar to what we want. So it efficiently calculates a row of the matrix of derivatives rather than a column. So it has an OM time complexity overhead to calculate the full derivative of a function from Rn to Rm, which is good if m is 1 and n is a billion. And for the space complexity, we again need to store all the intermediate values of f, right? For the same reason as we did in forward AD. And again, it generates a code that's linear in size as the original code. So I think I'll stop by showing what it does on a little example program. So this program performs a bunch of operations in row again. And now what you'll see for the code that this reverse AD algorithm generates is that it first runs the original program in the same order. And then what it does is it goes through the program in reverse order to calculate the derivative, right? So we ended by computing v from u1 and u2, and then we start the reverse pass to calculate the cotangents, so to calculate the action of the transpose derivative by first calculating the cotangent vector at u2, so u2 prime from the cotangent vector at v, and then we do, and we go through the program in reverse, really. And we see that at each step, we apply the chain rule and we replace a primitive operation with its transpose derivative. And then the final thing I'd like to note is we have a bunch of duplication happening in the original program. So we see that x4 is used twice. For example, it's used once to calculate y, and it's used once to calculate w. And we see that this duplication gets translated into addition of the cotangents, right? So we add the contribution of y to the cotangent at x4 and the contribution from w, right? Similarly, we add the contributions of w to u1 and u2. Where do we do that? Here, right? So we see that duplication becomes addition. So we're sort of mirroring the comonoid structure of duplication and dereliction to become zero and addition commutative monoid structure on our types of cotangents. I'd like to end here for today, and we'll look at more of the categorical aspects in the next two sessions. Are there any questions so far?
I have a question.
Mm-hmm.
So I'm surrounded by machine learning people at my home,
Mm-hmm.
and they're always throwing new buzzwords at me.
Mm-hmm.
So a lot of people talk about backpropagation, which
Yes.
I understood as just being chain rule, you know, a nice algorithm based on the chain rule. I'm trying to see the difference between reverse AD and backpropagation.
Oh, there's no difference. There's no difference. They're the same. Machine learning people tend to call it backpropagation.
Okay, thank
You
you.
can also call forward AD forward propagation.
So there's a question from Benjamin.
Mm-hmm.
Any chance to efficiently differentiate imperative code?
I haven't been looking at this yet, but some forms of imperative code, maybe you could hope you could differentiate like this. Of course, you can do a sort of store passing translation into a functional language first and then differentiating it using this technique. But I doubt that would be very efficient. So the honest answer is maybe not using this technique, but there are other techniques that people have used to efficiently differentiate imperative code, right? AD has been around since the 60s. It has primarily been applied to imperative code. But in this tutorial, I'm focusing on purely functional input programs and purely functional output programs with an eye to parallelism and correctness.
So I have a question. So you mentioned using functional programming for parallelism, but purity is only one ingredient, right? The real bottleneck is data dependencies. Any kind of comment on what happens with different AD algorithms with respect to data dependencies?
In what sense, data dependencies?
Do they destroy parallelization because they're introducing additional dependencies that you can't parallelize?
Well, the approach that I've been meaning to take is to build these algorithms, to implement these algorithms on top of established purely functional parallel programming frameworks like Accelerate or Futark. And I think that what you're referring to is a problem to do with parallelization that I guess these frameworks already solve, right? And then the AD just needs to not destroy it.
Thanks.
Maybe we can take that offline.
Yeah, sure.
I understand better what you mean.
Any more questions from the room? Yep.
Yeah. Mingshui Chen is asking, does it make sense to differentiate non-continuous programs?
I think this is a question I also wanted to.
Yeah, well, in certain ways, you can make sense of it, right? In a sort of senses of, I guess, distributional derivatives. But that's not the notion of derivative that I'm looking at here. But I know of at least one paper that I can link to that has been considering this sort of AD using distributional derivatives. But generally, we assume that things are continuous here. We assume that all our programs are differentiable. But the thing that I've really learned in STAN, in my practical work with people who who use automatic differentiation every day for probabilistic programming is that in practice, the difference between having a very large derivative and having a manageable derivative is just as bad as the difference between not being differentiable at all and being differentiable, or not even being continuous. So in some ways, we're in a quantitative world where the quantitative properties really matter rather than just the qualitative properties. Of course, we're working with floating point real numbers rather than genuine real numbers. So all our math is already a crude approximation of reality, right? Everything is finite precision in reality. So I think that mathematically the difference between continuous and differentiable and non-differentiable isn't so interesting in this context, because in some ways, having a very large derivative means you're not differentiable in any practical sense in applications. Rasmus Neugelberg is asking, is there a geometric interpretation to the reverse differentiable similar to the one for the forward differentiation? It's less intuitive maybe, but it's an operation that is the best extension of a function to cotangent vectors to propagate them backwards. Yeah, maybe I can send you a reference to make that more clear. But we'll look more at the mathematics behind this in the next session, both geometry and category theory.
Okay, so let's thank Matthijs again.